Welcome to Geography. I'm Mr. Ortega. Let's explore our amazing world together this time.
Today, Mars is a frozen, barren expanse. Red dust stretches endlessly to the horizon across a frigid desert that has remained desolate for billions of years. But high above that dust, satellite images reveal a different past. Scars etched into the terrain hint at ancient channels. Yet orbit has limits. Cameras identify physical shapes, but cannot analyze soil chemistry or answer if microbes survived there. To determine if Mars was ever truly habitable, the investigation required a physical presence on the surface to read the raw evidence. After a 7-month journey through space, the Opportunity rover touched down in January 2004. It landed in a flat, rock-strewn region known as Meridiani Planum. It wakes up for work by using its solar panels to capture energy from a sun positioned 140 million miles away. Opportunity operates as a robotic field geologist. It carries a specialized toolkit on its robotic arm. It is specifically designed to grind away the weathered surface of the terrain and expose the deep structural signatures hiding underneath. The layered bedrock outcroppings of Meridiani Planum preserve the physical history of early Mars. Almost immediately, the cameras revealed an anomaly littering the ground right in front of the vehicle: thousands of tiny, perfectly round spheres. These spheres, which the team quickly dubbed Blueberries, were about the size of BBs and embedded straight into the layered bedrock. When the rover ran its instruments over the spheres, it determined their composition: an iron mineral called hematite. On Earth, this specific spherical formation of hematite occurs naturally. It forms when rocks are soaked through with water. Finding these hematite blueberries embedded in the crust provides physical proof that the bedrock of Meridiani Planum was once saturated with liquid water. Proving the ground was wet was only the first step. The investigation next looked for signs of dynamic movement. Scanning the nearby outcroppings, Opportunity captured these distinct, layered ripples cut straight into the stone. When water actively flows across a sandy surface, it pushes the sediment into repeating wave patterns. Over billions of years, those shifting sands turned solid, fossilizing the current into stone. The geometry of these ripples confirms that the water wasn't just trapped beneath the dirt, it flowed across the surface of the planet. Knowing the water roved across the surface leads directly to the question of habitability. We need to know the chemical profile of that fluid. This chart compares the baseline chemistry of an Earth ocean to the data pulled from Meridiani Planum. The results reveal that the Martian water was exceptionally salty and highly acidic, effectively a sulfuric acid mixture. While a sulfuric acid sea would be toxic to human biology, specialized extremophile microbes on Earth thrive in identical chemical conditions. If a similar microbial organism existed on early Mars, this harsh, salty environment would have offered a viable, life-supporting habitat. A habitable environment requires one more variable to foster life: time. The data confirmed the water's presence, but the team still had to determine its duration. To find out how long the water lasted, the team sent their aging rover toward a massive, deeper crater where older geological layers lay exposed. Descending presented a severe physical risk. The rover had to meticulously creep down a steep, unforgiving incline covered in loose gravel, with no guarantee it could ever climb back out. As the vehicle moved lower, the chemistry and texture of the rocks changed. The composition of these deeper layers indicated that the bedrock had been soaked through for a continuous, extended period. The gamble paid off. The lower strata proved that the Martian water was not a brief, temporary flood. It persisted at Meridiani Planum for hundreds of thousands or millions of years. These observations, from the hematite spheres to the fossilized ripples and chemistry of the deep strata, redefined our understanding of Mars as a world where water once persisted for eons. This was possible because of the engineers and scientists at JPL who guided the rover every day, pushing the vehicle to its absolute mechanical limits. They successfully extracted an immense volume of physical evidence, returning hundreds of thousands of individual images and environmental readings back to Earth. That mountain of archival data is Opportunity's true legacy. There is enough recorded geological history to keep researchers busy for decades, meaning the mission's most important breakthroughs may still be waiting to be found. The process of reading the rocks and extracting history from a barren landscape now passes from the rover to you. Use the logic to analyze these geological features as you begin your own cartographic mapping challenge.